So thank you everybody for attending this session. As they mentioned, I'm Chester Leung. I'm one of the co-founders here at Opaque Systems, which is a startup building the confidential computing platform for collaborative analytics and AI. And just for some background, for years now, our team has been building and evangelizing privacy-preserving systems, in particular for analytics and AI, first in a research lab at UC Berkeley, and now here at Opaque. And along the way, we've learned numerous lessons about the trade-offs between different approaches, and perhaps more importantly, the practical barriers to adoption. And in this session, we'll be highlighting our most important learnings. But first, before we do that, let's actually challenge the premise. Why do we even care about privacy-preserving technologies? And the answer there that we've concluded is that organizations today have a ton of confidential data that is currently locked down in silos and that they are unable to fully derive value from. They cannot make this data available across teams within the same organization, let alone across different organizations. And as a result, a lot of the value that is inherent in this data is going untapped. And from what we've seen, this problem is not just isolated to one company or one sector. We've actually seen this problem repeat across multiple companies and across multiple sectors. For example, we've seen this in financial services, in telecom, in healthcare, and in ad tech. And the main problem that we just discussed is filled by privacy-preserving systems. They give us the ability to compute on sensitive data while keeping it encrypted, which in turn allows us to unlock the value of confidential data while maintaining its secrecy. And you may ask, why does this even matter? And we found that there are 3 high-level use cases that are pertinent today and that will be even more relevant tomorrow. First, organizations can accelerate their digital transformation and cloud adoption and move their confidential data workloads to the cloud without worrying about cloud misuse or exposure of their confidential data. Secondly, data owners can now collaborate with other teams within their business ecosystem. Each team can individually encrypt their data, pull it together in the cloud, and then jointly run analytics or AI on the collective data towards a mutually beneficial aim. Collaboration here enables the secure pooling of data, and as you all know, the more data you throw into an AI or analytic system, the better the insights will be. Thirdly, these technologies enable compliance with privacy laws and regulations like GDPR and CCPA that require private PII data to be protected while being processed by third parties. So now that we've set the stage for what problem this technology is solving and why it's inherently valuable, let's actually just take a step back to really get an understanding of what this technology is. For a while now, we were able to kind of think of data protection in 3 parts. First is being protected at rest. So for example, when the data is in storage. The second part is when data is in transit. So for example, when it's being sent over the network. And these 2 have really long been solved problems. So for example, databases have for a while now stored your data encrypted, and when you access the internet, the network communication is encrypted. The last part of data protection is the protection of data in use. And unlike the first 2, the protection of data in use is still not prevalent, which opens up an attack vector. The privacy-preserving systems that I'm referring to in this talk serve to protect the data while it's in use, which bridges this gap. So with privacy-preserving systems, there are 2 main approaches. There are cryptography-based approaches, and there are secure hardware-based approaches. Cryptography-based approaches include things like fully homomorphic encryption and secure multi-party computation. So when we're comparing on the efficiency and the security, on the efficiency side, the cryptography-based approaches are generally much slower. You can use specific approaches to tackle specific workloads, but these just aren't as generalizable. You can also use something like hardware acceleration, but the overhead will still remain. And really, to make these approaches practical for the big data workloads that many companies today are trying to support and run, the underlying math behind these cryptographic protocols would have to change. And this is something that even the leading cryptographers in the space are still trying to tackle. On the security side, the data remains encrypted throughout the lifecycle of the computation. But some cryptographic protocols, so for example, fully homomorphic encryption, do not provide integrity guarantees. You would need to add something like a zero knowledge proof here in order to really add this integrity guarantee to these protocols. On the other hand, trusted execution environments, which enable confidential computing, can actually support arbitrary workloads and leverage native processor speeds, which make them pretty much as scalable as plain text computation. They do, however, require a slightly larger trusted computing base in that you must have the trusted hardware. But like cryptographic protocols, the data computed on within the trusted execution environments remain encrypted in memory. TEEs are also, as some of you know, vulnerable to side channel attacks. So from what we've learned and from our discussions with numerous teams, researchers, data practitioners, the workload integrity as well as workload performance and scalability are critical must-haves for the analytics and AI that teams today are running. And as a result, we believe that TEEs running in the cloud with some additional cryptographic protection offer the best balance of security and performance. And while this conclusion that we've reached pretty much makes sense to everybody, it's unfortunately not as simple as trying out a technology on day one and then deploying it into production on day two. We've heard about numerous points of friction for the adoption of confidential computing, which we'll go over in the next couple slides. So from our experience over the years, there have been 4 common themes that have emerged. The first source of friction is that in addition to the security guarantees offered by TEEs, there needs to be more than just this security guarantees. So in particular, we've heard the following concerns when presenting confidential computing solutions to various teams. If these teams have if they've heard of TEEs before, the first question is usually around side channel attacks. If these teams have not heard of TEEs before, but they have some security or cryptography experience, the question is then usually around the verifiability of the computation. And if these teams are working on a project that involves sharing data with another team or organization, the question is usually around governance of that collaboration. And in particular, how agreed upon policies and processes are enforced. We've seen that many teams are becoming more and more interested in this concept of secure collaboration because of its potential to unlock novel insights. As a result, any solution, and in particular a solution that enables secure collaboration, must offer multiple layers of security on top of those offered by TEEs. So these should include cryptographic fortification to patch side channel attacks. They should also offer a simplified interface on top of mechanisms like remote attestation to verify workloads. And these solutions should also provide a means to collaborate with visibility and enforcement of collaborator actions. So that was the first point of friction. The second point of friction that we've seen is the need for these solutions to integrate deeply into existing analytics and AI workflows and tools. To minimize friction, confidential computing solutions must look and feel like the tools that data practitioners use today. In particular, they should have similar, if not identical interfaces, expose the same APIs with the same underlying functionality, and integrate with the data sources and data visualization tools that are commonly used today. And moreover, the deployment should be as similar as possible to deployments today. So really this point is around abstraction. All the additional security features and the infrastructure differences should be abstracted away. The third barrier to entry here is really around governance, and in particular, how to govern data sharing in a collaborative scenario. So as we mentioned a bit earlier, one huge use case of confidential computing is multi-party collaboration, where multiple entities with confidential data securely share data to achieve some outcome. So for example, we could have multiple divisions within a bank, which obviously holds very sensitive data and prohibits cross-division sharing of data. And these multiple divisions may want to, for example, work together for fraud detection. And with collaboration, we've often heard the following questions come up. How do I make sure that other parties aren't just dumping my entire data set? Can I control what the other collaborators see? And how do I know what other parties are doing in this collaboration? So for all these questions, we've kind of reached the same conclusion. And the answer is that any secure collaboration solution needs to offer something that we are calling policies, which as we define it is an auditable mechanism to ensure that all parties have full visibility into what every other collaborator can and cannot see and can and cannot do. So as a couple of examples of what these policies are, one example is data policies, which could be something that allows you to apply conditions or expressions to limit your data that can be accessed by other parties. Another example could be computation policies, which will limit what can and cannot be run on your data. And the last example is output policies, which limit who can see the results of specific jobs. So moving on to the last source of friction now, this main point is around scalability, not just in terms of kind of compute, but also on a number of axes. We've seen, that cryptographic approaches like fully homomorphic encryption and secure multi-party computation are a bit more well-known and tried at this point. But most, if not all the teams who are trying to run today's AI and analytic workloads are reaching the same conclusion, and they've actually shared this with us. And that conclusion is that these cryptographic-based techniques are just too slow for the amount of data and the types of computation that needs to be run. Confidential computing, on the other hand, relies on hardware to offer the confidentiality and the integrity of data and the integrity of code, and as a result has much less overhead. So for example, a secure SQL analytics engine that we've developed here at Opaque is only up to 2 times slower than the completely insecure alternative on an entire suite of business-oriented queries. And in addition, the growing maturity of the confidential computing ecosystem, which we've kind of seen throughout OC3, means that there are projects being built out up and down the stack that enable ease of configuration, setup, and orchestration, and even can offer simplified multi-cloud support. So just to toot our horn here at Opaque a little bit, at Opaque, we built a platform that has addressed all 4 of these concerns. The platform offers multiple layers of security, integrates with familiar tools, offers mechanisms for secure collaboration, and lastly, scales seamlessly across clusters and teams. So this is the end of this talk. Thank you so much for coming to this session, and hopefully, we were able to share some insights that you found useful.